Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. In episode 103 of the Network Plus Prepcast, we're focusing on an essential conceptual layer of routing, the difference between interior and exterior routing protocols. Understanding routing scope helps define where specific protocols are intended to operate, how they behave, and how they interact. Networks are rarely isolated systems. They connect to other networks, service providers, or even the public internet. Routing must scale, adapt, and enforce control based on where data is flowing, and this is why scope matters. Knowing whether a protocol is designed for internal use or external communication is vital for both configuration and troubleshooting. When we talk about routing scope, we refer to the administrative boundaries within a network. At the most basic level, there are two scopes, interior and exterior. Interior routing occurs within a single organization, often across multiple sites or departments. Exterior routing occurs between separate organizations or networks, typically across the public internet. Choosing the correct protocol for each scope ensures that routers can make efficient path decisions, honor policies, and maintain both speed and stability. This distinction not only simplifies network architecture, but also enhances scalability and security in both enterprise and service provider environments. An interior gateway protocol, or IGP, is used for routing within a single organization's domain. These protocols are designed for internal communication and are optimized for speed and rapid convergence. IGPs share routing information across routers under common administrative control. Examples include OSPF, EIGRP, and RIP. Each of these protocols handles path selection, metric calculation, and failure recovery for internal traffic. They operate based on trust without requiring complex policies or external negotiation. IGPs are the backbone of LAN and WAN routing inside most enterprise networks. Let's explore the most common IGP examples. Open Shortest Path First is a link state IGP that builds a complete map of the internal network to make intelligent routing decisions based on cost. It supports hierarchical design through the use of areas and converges quickly after changes. Enhanced Interior Gateway Routing Protocol is a Cisco proprietary hybrid IGP that uses multiple metrics, such as bandwidth and delay, to calculate composite path scores. It's known for rapid convergence and route summarization. RIP, the oldest of the three, is a distance vector IGP based on hop count, suitable only for smaller educational networks. Exterior Gateway Protocols, or EGPs, operate between different administrative domains. Their purpose is to manage how routes are exchanged across autonomous systems, collections of routers controlled by different organizations. BGP, or Border Gateway Protocol, is the dominant EGP and is used across the internet. EGPs enable organizations to connect, share routing information, and enforce complex policies based on business relationships, such as which paths to accept, prefer, or avoid. Unlike IGPs, which assume trust, EGPs operate under the assumption that peers may not be fully trustworthy. Routing domains are defined by administrative boundaries, and they are often associated with autonomous system numbers, or ASNs. An AS is a group of routers under common control, typically belonging to one organization or service provider. Each AS is assigned a unique number that identifies it on the global routing table. These boundaries dictate which protocol is used. AGPs are used within the AS, and BGP is used between ASES. The presence of multiple ASES in a network topology means routing behavior, protocol choices, and security policies must reflect these domain boundaries. BGP serves a unique and powerful role as an EGP. It does not rely on hop count or internal metrics, but instead selects routes based on path attributes and administrative policies. The most notable of these is the AS path, which records the sequence of autonomous systems a route has traversed. This helps prevent routing loops and allows organizations to implement route preferences based on external factors. BGP is designed for stability and predictability. ensuring that internet web routing decisions do not change abruptly or frequently, even if internal paths change. One of the biggest differences between IGPs and BGP is the level of administrative control. Within an IGP, administrators have full control over all routers and the entire routing domain. This allows for consistent policies and predictable behavior. BGP, in contrast, involves negotiation between peers. Each side chooses what routes to advertise or accept based on its own rules, and may apply filters or preferences to enforce those decisions. There's no centralized control in BGP, making its behavior more complex and policy-driven compared to interior protocols. Convergence behavior is another area where IGPs and BGP differ significantly. IGPs are optimized for rapid recovery from changes. They use triggered updates and topology awareness to recalculate paths in seconds or less. BGP, however, prioritizes stability. Its convergence can take minutes, especially when global routing updates are involved. This delay is intentional. It reduces flapping and prevents instability from propagating across the internet. BGP confirms path validity using route attributes and timers, ensuring that only the most stable and trustworthy routes are installed. Autonomous system numbers are essential to understanding routing scope. Public ASNs are assigned by regional internet registries and are used when a network participates in global BGP routing. Private ASNs are used within an organization's internal BGP configuration and are not propagated across the internet. Each AS acts as a unique identifier for a routing domain and is required for BGP operation. Proper use of ASNs ensures that routing loops are avoided and that each path across the internet is traceable to its source and destination. Finally, there is significant interaction between IGPs and BGP within many organizations. Routes learned through BGP are often redistributed into an IGP so that internal routers can forward traffic properly. Likewise, selected internal routes may be advertised to BGP peers. This redistribution must be handled carefully to avoid loops, route leaks, or conflicts. Route filtering, tagging, and path control mechanisms are essential tools for managing these interactions and ensuring that routing information is consistent and secure across the boundary between interior and exterior protocols. One of the core differences between interior and exterior routing protocols lies in the metrics they use to make routing decisions. IGPs such as OSPF, EIGRP, and RIP rely on metrics like hop count, bandwidth, delay, reliability, and cost. These metrics are used to determine the most efficient or optimal path through the internal network. In contrast, BGP does not rely on performance metrics but instead uses administrative attributes to determine routing decisions. These include the AS path length, local preference, origin type, and the multi-exit discriminator. Each of these values influence which path is preferred when multiple routes are available. While IGPs aim for speed and accuracy in path selection, BGP focuses on stability and adherence to routing policies. BGP is not optimized for rapid convergence, it's built for controlled decision-making. The protocol allows administrators to apply routing policies that match business objectives or technical constraints, such as preferring one upstream provider over another or preventing certain prefixes from being advertised externally. These policies can be enforced using route maps, prefix lists, and filter rules, enabling fine-grained control over the flow of traffic between autonomous systems. Scalability is another major differentiator between interior and exterior routing protocols. IGPs are typically optimized for environments like local area networks or private wide area networks, where the number of routers and prefixes is limited. Their use of fast convergence and limited scope makes them unsuitable for handling internet-scale routing. BGP, however, was specifically designed for such scalability. It is capable of handling tens of thousands of prefixes, supporting large enterprises and global internet backbones. Each protocol type must be tuned differently to handle its scale, and knowing these differences is key to protocol selection. When troubleshooting issues in environments where both IGPs and EGPs are used, understanding scope boundaries is critical. Problems such as unreachable prefixes, routing loops, or unexpected path selection often stem from misconfigured redistribution or missing filters. Tools such as route maps, prefix lists, and administrative distance settings help control how routes are imported and exported between protocols. Administrators must be able to determine whether an issue is internal, within the IGP domain, or external, involving BGP peers or internet connectivity. Diagnosing these scope-based problems accurately ensures a quicker and more targeted resolution. Security plays a significant role in managing routing scope. Inside an IGP domain, routers generally trust one another and share all routing information. However, at the boundary between autonomous systems, trust must be earned. BGP peers often filter incoming routes to prevent the advertisement of bogons, invalid or reserved IP ranges, and apply prefix limits to guard against route table overflow. These filters help prevent accidental or malicious route advertisements that could disrupt connectivity. Inside an IGP, simpler controls, such as passive interfaces or authentication, are used to secure route exchanges between trusted routers. Multi-homing is a common practice that highlights the need for both IGPs and EGPs. In a multi-home environment, an organization connects to more than one internet provider for redundancy or load balancing. BGP is used to manage these external routes, selecting the best provider path or advertising preferred prefixes. Inside the organization, an IGP maintains internal path integrity and failover. Together, the protocols ensure both outbound traffic flow and internal consistency. Managing failover and redundancy across these boundaries requires careful planning, route summarization, and path control logic. Choosing which protocol or scope to apply depends on the size of the organization, the level of control required, and whether external connectivity is involved. A small business with a single ISP and one or two routers might not need BGP at all. A medium-sized enterprise with branch offices and multiple ISP connections may need to run both OSP, F, and BGP in different parts of the network. A global provider with thousands of prefixes and peer agreements must rely heavily on BGP for external routing and enforce strict internal routing policies using IGPs like OSPF or EIGRP. In summary, understanding routing scope helps clarify which protocol to use, where to use it, and how protocols interact at the edges of administrative domains. Interior gateway protocols provide fast, scalable, and trusted routing within an organization, relying on performance-based metrics and full administrative control. Exterior gateway protocols like BGP support routing exchange between independent systems using policies, attributes, and path verification to maintain stability and enforce control. Successful network design requires proper separation, coordination, and integration of these routing domains. To conclude, the distinction between interior and exterior routing protocols is essential for both certification and real-world implementation. Interior gateway protocols like OSPF, EIGRP, and RIP handle communication within a single administrative domain using performance metrics and rapid convergence. Exterior gateway protocols, primarily BGP, manage connectivity between autonomous systems, with a focus on policy, stability, and scalability. Recognizing the scope of each protocol and their roles in enterprise and internet routing is key to designing, managing, and troubleshooting modern network infrastructure. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cyber Security Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.